The first signs appeared quietly, not with dramatic headlines, not with emergency alerts, not with images of towering storm clouds spreading across television screens. Instead, they appeared inside weather models. Small changes, subtle shifts, numbers moving in directions that meteorologists did not expect to see this early in the season. At first, they looked insignificant: a slight increase in atmospheric instability, a growing temperature anomaly, an unusual pattern developing across thousands of miles of ocean and land. Individually, none of these signals seemed alarming, but when scientists combined them into a larger picture, something extraordinary began to emerge. A summer weather system unlike anything seen in recent years was beginning to take shape, and it was growing stronger. Meteorologists around the world started paying attention. Weather centers increased monitoring. Climate specialists reviewed historical records. Forecast teams ran simulation after simulation. The reason was simple: the atmosphere was beginning to organize itself into a pattern capable of influencing weather across enormous regions. Not for days, not for a single week, but potentially for an entire season. What made the situation remarkable was not a single storm. It was not one heat wave. It was not one drought. It was the possibility that all of these events could become connected by the same atmospheric engine, a system powerful enough to influence temperatures, rainfall, severe storms, and even wildfire conditions across vast areas. As summer approached, researchers noticed that the jet stream was behaving differently. Normally, this fast-moving river of air high above the Earth helps guide weather systems from one region to another. It acts like a highway in the sky. Storms follow its path. Temperature patterns respond to its position. Seasonal weather often depends on how stable it remains. But now the jet stream was beginning to bend. Large waves were developing. These waves appeared stronger and more persistent than normal. Instead of moving steadily, some sections began slowing down. Others became locked into place. When that happens, weather conditions below can remain unchanged for extended periods. Heat stays trapped. Rain continues falling. Drought intensifies. Storms repeatedly target the same locations. Meteorologists know that when atmospheric patterns stall, the impacts can become severe. As more forecast data arrived, confidence increased that this was not a temporary fluctuation. A larger process was unfolding. Across several regions, temperatures were already rising above seasonal averages. Some locations experienced unusually warm nights. Others reported humidity levels increasing earlier than expected. Warm ocean waters were adding additional energy into the atmosphere. That energy had to go somewhere, and weather systems were preparing to use it. One forecasting center compared the developing pattern to some of the most memorable summers in modern records, not because the exact conditions were identical, but because the atmosphere showed similar warning signs: persistent heat, amplified pressure systems, increased instability. The ingredients were assembling. The question was not whether the atmosphere would respond. The question was how extreme that response would become. Meanwhile, residents in several regions noticed subtle changes. Days felt hotter. Evenings remained unusually warm. Air masses that normally moved away lingered longer than expected. Weather forecasters began using new language in their discussions. Words like persistent, anomalous, and high impact appeared more frequently. These terms are not used casually. They signal growing concern. As summer sunlight intensified, the atmosphere absorbed more energy each day. Ground temperatures climbed. Surface heating accelerated. The difference between cooler and warmer air masses became more pronounced. This contrast is important. Many severe weather events depend on it. The greater the difference, the greater the potential energy available for storms. Across large sections of the continent, soil moisture conditions also began influencing forecasts. Dry ground heats faster than moist ground. When extensive areas become dry, temperatures can rise even more rapidly. This creates feedback loops. Heat produces dryness. Dryness produces more heat. The cycle strengthens itself. Meteorologists watching the developing pattern realized that multiple atmospheric mechanisms were beginning to align. Each one alone could influence summer weather. Together, they could produce something much larger. At the same time, ocean temperatures remained under close observation. Oceans store enormous amounts of energy. Even small temperature changes across vast stretches of water can influence weather thousands of miles away. Researchers noticed that certain ocean regions were warmer than average. Those warm waters increased evaporation. More moisture entered the atmosphere. That moisture eventually becomes fuel. Fuel for thunderstorms, fuel for heavy rainfall, fuel for large-scale weather systems. The atmosphere was collecting resources: energy from the sun, moisture from the oceans, heat from the land. Everything was building. Weather models began showing scenarios that caught forecasters' attention. Some simulations suggested prolonged heat events. Others indicated heightened severe storm activity. Several pointed toward increased rainfall extremes. No single outcome appeared certain, but nearly all scenarios shared one conclusion: the atmosphere was becoming more volatile. As June progressed, pressure systems started arranging themselves into recognizable formations. High-pressure ridges expanded. Low-pressure troughs deepened, the contrast between them strengthened. Meteorologists often compare these features to hills and valleys in the atmosphere. The steeper those hills and valleys become, the more dramatic weather conditions can grow beneath them. In several forecast runs, these features became exceptionally pronounced. The patterns lingered. They resisted change. That persistence worried experts, because persistent patterns often produce persistent impacts. A heat wave lasting 2 days is uncomfortable. A heat wave lasting 2 weeks becomes dangerous. A month-long heat event can become historic. The same principle applies to rainfall. Repeated storms over the same area can overwhelm rivers, reservoirs, and drainage systems. Duration matters, and the developing summer pattern appeared capable of extending weather extremes far beyond normal expectations. Communities began preparing. Emergency managers reviewed response plans. Utility companies monitored power demand forecasts. Agricultural experts assessed potential impacts on crops. Water resource managers examined reservoir conditions. Everyone understood the same reality. Extreme weather affects more than temperature. It affects infrastructure, food production, transportation, public safety, energy systems, and daily life. Meanwhile, atmospheric scientists continued gathering data. Weather balloons launched into the sky carried instruments through layers of the atmosphere. Satellites monitored cloud development, moisture transport, and temperature distributions. Supercomputers processed enormous volumes of information every day. Each update refined the picture. And with each update, confidence continued growing. The atmosphere was entering a highly energized state. In some areas, residents were already experiencing early examples of what might come. Strong afternoon thunderstorms developed rapidly. Heavy rain fell over short periods. Localized flooding appeared. Temperatures surged above seasonal averages. These events alone were not unusual. Summer often produces such conditions. What concerned forecasters was their frequency. The atmosphere seemed increasingly ready to generate them, again and again, across wider regions, for longer durations. The developing weather system was not a single event moving across a map. It was something broader, a pattern, a framework capable of producing multiple extremes: heat, storms, heavy rainfall, drought, wildfire conditions, all depending on location, all connected through the same atmospheric structure. As scientists compared current conditions with historical records, they found similarities to several notable summers, not exact matches. Weather never repeats perfectly, but the signals were familiar enough to attract serious attention. The combination of elevated temperatures, atmospheric instability, and persistent circulation patterns had appeared before, and when it had, the results were often significant. Forecast discussions became increasingly detailed. Meteorologists emphasized uncertainty where appropriate. They avoided making exaggerated claims, but they also acknowledged the growing evidence. The atmosphere was preparing for a potentially remarkable summer. One expert summarized the situation carefully. The ingredients are present. The atmosphere is becoming increasingly supportive of prolonged extreme conditions. That statement reflected the consensus forming among many forecasting teams. No one could predict every outcome. No one could identify every location that might experience impacts. But the broader signal was becoming difficult to ignore. Something large was developing, something powerful, and something capable of reshaping weather patterns across enormous areas. As July approached, additional data began arriving from observation networks around the world. Each new data set added detail to the picture. The atmospheric pattern was not weakening, it was strengthening. Pressure systems became more organized. Temperature anomalies expanded, moisture transport increased. The structure continued evolving. And with every passing day, meteorologists devoted more resources to understanding what might happen next. Because this was no longer simply a forecast challenge, it was becoming a seasonal story, a developing weather pattern with the potential to influence millions of people. The atmosphere had not yet reached its peak intensity. The most significant phase had not yet arrived, but the foundation was already in place. The energy was building, the signals were aligning, and the most extreme part of the summer weather system was still ahead. By the time meteorologists entered the middle of summer, the atmosphere had already begun showing the first signs of the pattern they had been tracking for weeks. What had once existed only inside computer simulations was now appearing in real-world observations. Temperature records were being challenged. Humidity levels were increasing across large regions. Storm systems were becoming more organized, and weather experts were watching closely as the developing pattern continued to strengthen. The atmosphere operates like a massive interconnected machine. Every change influences something else. A warming ocean affects moisture levels. Moisture affects cloud formation. Cloud formation affects temperature distribution. Temperature differences influence pressure systems. Pressure systems guide storms. Everything is connected. And during this summer, many of those connections were becoming unusually active at the same time. Across several regions, high-pressure systems expanded dramatically. These atmospheric ridges acted like giant domes. They trapped heat near the surface. They reduced cloud development. They limited rainfall. And because they remained in place for extended periods, temperatures continued climbing day after day. Normally, weather systems move. A few hot days are often followed by cooler conditions. A ridge shifts, a front arrives, temperatures moderate. But this time, the atmosphere appeared reluctant to change. The same pattern remained locked into position. As a result, heat accumulated. Each morning began warmer than the one before. Each afternoon pushed temperatures higher. Each evening provided less relief. Meteorologists began noticing another concern. Nighttime temperatures were remaining unusually elevated. This may sound insignificant, but overnight cooling is extremely important. It allows the environment to recover. It gives infrastructure a chance to cool. It reduces stress on electrical systems. It helps people rest. When nighttime temperatures stay high, the effects of daytime heat become much more severe. The atmosphere was no longer simply producing heat. It was holding on to it. At the same time, another process was unfolding. Large amounts of moisture were moving northward from warm ocean regions. Satellite imagery revealed enormous plumes of humid air stretching across thousands of miles. This moisture served as fuel. Whenever it encountered unstable atmospheric conditions, storms rapidly developed. Some areas experienced intense thunderstorms. Others received torrential rainfall. In certain locations, rainfall totals that would normally accumulate over several weeks fell within hours. Emergency officials monitored rivers and streams. Urban drainage systems struggled to keep pace. Roadways flooded, low-lying areas filled with water. Meteorologists emphasized that the atmosphere's increased moisture content was a key factor. Warm air can hold more water vapor. The warmer the atmosphere becomes, the greater its ability to store moisture. When that moisture is eventually released, rainfall intensity often increases. This relationship had become increasingly visible. Storms seemed capable of producing extraordinary amounts of rain in very short periods. Weather radar images displayed massive thunderstorm complexes expanding across entire regions. Lightning activity increased. Wind reports became more frequent. Severe weather warnings appeared with greater regularity. The atmosphere was demonstrating just how much energy it had accumulated. Meanwhile, agricultural communities were experiencing a different side of the pattern. In some regions, persistent heat and limited rainfall created growing concerns about soil moisture. Fields dried rapidly, water demand increased. Farmers monitored forecasts closely. Agriculture depends heavily on predictable weather. When patterns become extreme, planning becomes difficult. One week might bring intense heat. The next could deliver severe storms. The variability itself becomes a challenge. Across forested regions, wildfire concerns also grew. Dry vegetation combined with prolonged heat created favorable conditions for fire development. Land management agencies increased monitoring efforts. Fire weather forecasts received additional attention. Meteorologists understood that heat alone is only part of the equation. When combined with low humidity, dry fuels, and strong winds, the risk can increase significantly. As summer progressed, the atmosphere continued reinforcing itself. The same large-scale circulation pattern remained dominant. The jet stream showed little sign of returning to its normal behavior. Instead, large atmospheric waves persisted. These waves helped maintain the extreme conditions developing beneath them. Scientists often compare the atmosphere to a river. When the river flows smoothly, weather patterns move efficiently. When the river develops large bends and slow-moving sections, conditions become stagnant. That stagnation was becoming one of the defining characteristics of the season. The persistence of the pattern surprised even experienced forecasters. Weather systems that should have moved away remained in place. Heat lingered. Storm tracks repeated. Rainfall focused on the same regions. The atmosphere seemed trapped within its own structure. Meteorological agencies around the world exchanged data continuously. Forecast centers compared model results. Research institutions analyzed emerging trends. Every update reinforced the same message. The summer pattern was not weakening, it was intensifying. Ocean observations provided additional clues. Sea surface temperatures remained elevated in several key regions. These warm waters continued supplying energy to the atmosphere. Moisture transport increased. Instability expanded. Thunderstorm development became more efficient. The atmosphere was functioning like an engine operating at higher power. Every available source of energy was contributing. As temperatures continued rising, demand for electricity increased sharply. Air conditioning systems operated for longer periods. Power grids experienced higher loads. Utility providers monitored consumption carefully. Extreme weather affects far more than outdoor conditions. It influences infrastructure, economics, and public safety. The impacts ripple outward through entire communities. Health officials also issued guidance. Extended periods of heat can place significant stress on vulnerable populations. Hydration becomes critical. Cooling centers may be activated. Public awareness campaigns often emphasize preparation and caution. Meteorologists repeatedly stressed that extreme weather is not measured only by record-breaking temperatures. Duration matters. A moderately severe event lasting weeks can become more impactful than a short-lived extreme event. This summer was demonstrating exactly why. The atmosphere showed little interest in resetting. Every forecast cycle seemed to extend the persistence of the pattern. As July moved forward, severe weather outbreaks became increasingly organized. Clusters of thunderstorms merged into larger systems. These complexes traveled across vast distances. Some produced damaging winds, others generated heavy rainfall. Several regions experienced repeated rounds of storms over short periods. Meteorologists described the atmosphere as highly primed. Energy values remained elevated, moisture levels stayed abundant, instability persisted. Whenever triggering mechanisms developed, storms responded quickly. The atmosphere seemed ready to convert stored energy into weather with remarkable efficiency. Researchers studying historical weather records noticed similarities to some of the most notable summers of the past. Again, no 2 years are identical, but the structure of the atmosphere shared characteristics with seasons remembered for significant weather impacts. Persistent ridges, strong temperature anomalies, enhanced moisture transport, extended periods of instability. The pattern was becoming increasingly recognizable. What made this situation particularly unusual was its geographic scale. The atmospheric structure influenced enormous areas simultaneously. Some locations experienced prolonged heat, others dealt with excessive rainfall, still others alternated between both extremes. Different outcomes emerged from the same overarching system. Meteorologists frequently reminded the public that weather is rarely uniform. One region can experience drought while another experiences flooding. One area can endure record heat while another remains unusually wet. Yet all may be connected through the same atmospheric framework. That framework continued strengthening. By late summer, forecast discussions became increasingly focused on longevity. The central question was no longer whether the pattern existed. Its presence was obvious. The question had become how long it would remain dominant. Every additional week increased the likelihood of cumulative impacts. Heat stress builds, water resources change, infrastructure experiences greater strain. Agricultural effects become more pronounced. The atmosphere was creating consequences, not through a single dramatic event, but through sustained influence. Scientists continued collecting observations around the clock. Weather balloons sampled atmospheric conditions. Aircraft gathered specialized measurements. Satellites provided global coverage. Supercomputers processed vast amounts of information. The resulting picture remained remarkably consistent. The pattern persisted. The atmosphere remained energized, and the potential for significant weather impacts continued. As August approached, some meteorologists began describing the season as one of the most dynamic in recent memory, not because every location experienced extremes, but because the atmosphere itself had entered a highly amplified state. Large-scale processes were interacting continuously. Energy transfers remained active. Moisture transport stayed elevated. Instability never seemed far away. The summer weather system had evolved from a developing forecast into a defining seasonal event. Communities adapted as best they could. Emergency managers adjusted plans. Utilities increased preparedness. Agricultural sectors monitored changing conditions. Researchers continued analysis. Everyone recognized the same reality. The atmosphere was operating differently, and the effects were being felt across vast areas. Yet despite everything that had already occurred, meteorologists remained cautious. They understood that seasonal weather patterns can change. New influences can emerge. Atmospheric structures eventually shift. But at this moment, all available evidence pointed toward continuation rather than relief. The engine driving the summer remained active. The heat remained present. The moisture remained abundant. The instability remained elevated. And the atmosphere continued demonstrating its extraordinary capacity for extremes. The most remarkable aspect was not any individual storm, not any single heat wave, not any isolated event. It was the scale, the persistence, the interconnected nature of the entire system. A weather pattern powerful enough to shape conditions across enormous regions for an extended period of time. And as forecasters examined the latest model data, one conclusion became increasingly difficult to ignore. The atmosphere had not yet fully exhausted its energy. The summer weather system was still active, still evolving, and still capable of producing significant impacts before the season finally came to an end.